So what we have been discussing so far is basically being able to solve the system of linear equations, say x is equal to b. Existence, uniqueness, and all that stuff is settled. We saw LU and QR as two methods to compute the solution. Okay, compute x. How do you compute x? And now we want to start with sensitivity analysis. Correct. So this sensitivity analysis, why is it required? We had a discussion about it in last week's class. So now with that motivation in our mind, now we want to study sensitivity analysis. And in sensitivity analysis, first thing that we want to look at is matrix norms. Okay, so so this matrix norms is really very important, because they will actually be the tool with which we will quantify how much is the perturbation or how far away you are, what is the degree of error that you are introducing. Okay, so that measure or that gauge of these things, we need some quantification. So that quantification will be provided by matrix norms. Okay, so there are several types of matrix norms. So there are two interpretation of matrices. Okay, so matrices, basically you can view them as vectors. Correct. So matrix are m by n. I think that's the size we are taking, m by n, and in particular if it is square, it's m by n. So matrices basically are of the arrays of the size m by n, and you can view them as vectors in Rmn. Correct. By doing the operation of vectorization. I think this you understand now after watching video given by Sumanta also. How will you convert matrix into a vector? You just put one column below the other, stacking columns one below the other. You can convert the matrix into a vector. So you can actually think of matrix as a one-dimensional, very long one-dimensional array. But there is interesting property attached to matrices, which is it's a linear transformation. Is a linear transformation from Rn to Rm as well. Correct. So this is a linear transformation from Rn to Rm. So every x in Rn, so every x in Rn gets transformed to Ax in Rn. Correct. So that is the transformation. That is the linear transformation that you're looking at. So these are the two different interpretation of matrices. One is viewed as a vector, and the other is linear transformation from Rn to Rm. And with these two different interpretations, we'll introduce two different types of norms also. Okay, and naturally we will see how these norms come about. Okay, so first norm is Frobenius norm. So okay, so before we go further, just quick reminder of what is a norm. So I hope you all remember the definition for norm of vectors. We can continue with that definition. There is one slight addition. Okay, we need one more condition for matrix norm. Okay, so for every a in Rn by n. Okay, so let us start with square matrices, then we will as usual generalize these things to matrices which are non-square roots. Okay, so for every a b matrices in Rn by n, some scalar alpha beta in R, what are the properties of matrix norm? So the first thing is matrix norm is always greater than or equal to 0, and this is 0 if and only if A is equal to 0. So this is the condition that you had already seen. The second condition is norm of alpha A is mod alpha norm A. This is also vector norm condition that you had seen. The third condition is A plus B is less than or equal to norm of A plus norm of B. This is triangle inequality. This is also present in case of uh, vector norms. But this fourth property is something that is new, that is extra added for n by n square matrices, which says that product of AB, okay, norm of product of AB has to be less than or equal to norm A into norm B, and this property is called as submultiplicativity property. Okay, so this is the extra property that gets added, submultiplicativity, and with these four properties, any function which satisfies these properties, so this function from Rn cross n to R with these properties, this property is called as norm function of matrices, right? So the simple examples of norms. So the first example is Frobenius norm. Okay, so this Frobenius norm, how do we define? We define it to be norm of A. I denote it with a subscript F. Summation I from 1 to n, summation j from 1 to n, mod A I j square whole to the power half. So this is called as Frobenius norm. So this defines a norm. This is called as Frobenius norm. And now you can see this norm is generated. This norm is basically coming out because of what? Two norm. It's a spectral norm of a vector of size n square. Correct? And what is this vector of size n square? This is the vector of size n square which you will obtain after you put columns of A one below the other. Right? So this type of norm, the Frobenius norm that you see here, is actually coming out. It is motivated after looking at matrix as a vector. Okay, if you view at matrix as a vector, the only thing that I think now we will need to check is the submultiplicativity property, and the submultiplicativity property you can prove very easily using Cauchy-Schwarz inequality, right? Since 2 norm is a norm on n Rn square, first three properties of norm are automatically satisfied. First three properties of matrix norm are automatically satisfied. For submultiplicativity, we use Cauchy-Schwarz inequality. Okay. So how do we use Cauchy-Schwarz inequality? So let us see C is equal to AB, the product. Then Cij is actually summation k from 1 to n, Aik Bkj, right? Where A is actually Aij, B is actually Bij, and C is actually Ci. Right, so this is how I denote the matrices, and then what will happen? This is the Cij entry, and I'm interested in looking at norm of this product AB, right? Frobenius norm. So I start with Frobenius norm of AB square, which is nothing but Frobenius norm of C square. Correct. So by definition, what is it? By definition, it is I is equal to 1 to n, j is equal to 1 to n, and mod Cij square, right? So now the trick is to write down what is Cij square. So this is I from 1 to n, j from 1 to n, and then mod Cij square, I will write down k from 1 to n, Aik Bkj square. And now I'll apply Cauchy-Schwarz inequality, and the Cauchy-Schwarz inequality says that this is less than or equal to summation I from 1 to n, summation j from 1 to n, and then you have summation mod Aik square, correct? So k from 1 to n. So I'm applying Cauchy-Schwarz inequality to this fellow, right? Into summation k from 1 to n, Bkj square. Is that right? So that is where I have applied Cauchy-Schwarz inequality for this part. Red highlighted part, I apply Cauchy-Schwarz inequality. and using Cauchy-Schwarz inequality I get this. And this I can write down as summation I from 1 to n, summation k from 1 to n, aik square, and this is 1, and summation j from 1 to n, summation k from 1 to n, bkj whole square, which is nothing but norm of a square times norm of b square Frobenius norm. So which proves that submultiplicativity property, proving that this matrix, this norm is actually a matrix norm. So this implies that this Frobenius norm is a matrix norm. So this is the definition of norm. This is the definition of matrix norm that arises because of viewing this as a vector, because of viewing matrix as a vector. Okay, so Cauchy-Schwarz inequality, right? So this is the key. So you being able to use Cauchy-Schwarz inequality is the key, and with that we prove this particular thing. Any doubt about this? So this particular function is a norm, matrix norm. Okay, then we move further, and now we introduce some norm viewing the matrix as a linear operator. Okay, so viewing the matrix as a linear operator, we induce norm through the action of this matrix on its vectors, right? So that is what we really want to do. So for example, I'll just define this first, A2 norm to be equal to maximum of x not equal to 0, norm of ax divided by norm of x. Okay, so this is the function that I define, right? So for every a and for every x, so for every a in R n by n, right? So for every a in n by n matrix set, I define this function like this. So is this function a norm? So the question is this function a norm? So what can you say? Is this function a norm? So what is happening here? Do you understand how I am defining this particular thing? I am defining it through the action of matrix A on the vectors x, right? So on the right hand side, if you see the numbers appearing in numerator as well as denominator, what are they? The numbers appearing in numerator as well as denominator, they both are vector norms, right? And where are these vectors coming from? So these vectors are coming from norm of ax. So you look at the image of x and you look at the vector x itself, and you look at the ratio of norms of image to the vector itself, right? So that is what you are really looking at. Now if you see this, then you tell me what we are really looking at here. Can you see geometrically what is really happening? So every vector x in Rn goes to a vector ax in Rn. You look at the norm of this vector, you look at the norm of this vector, and you look at the ratio of these norms. What is this ratio basically telling you? Norm of ax.
The scaling factor.
Scaling factor, correct. So this ratio is telling you the scaling factor. How much is the magnification or scaling happening to vector x, right? So x changes to ax, we know. And we saw one example where the magnification or scaling was really very big, or magnification or scaling was really very small. So A will induce different scalings in lengths to the length of vector x, right? So you are looking at all these ratios which are kind of indicating magnification or scaling induced by x in the image space. And what are you looking at? You are looking at maximum of all such things. And obviously you will not take x is equal to 0, because 0 goes to 0 under any linear transformation, we know that. So 0 doesn't get scaled at all. 0 remains 0. So we don't have to worry about 0. So this is what you are really looking at. You are looking at the magnification induced by So this we will call magnification induced by A in X. Okay, and how does magnification induced by A in X? How will A induce that magnification? A will induce that magnification by action AX, correct? So this is the action AX. A takes action on X, you get AX, and that's how you really look at. So this is the thing that we are really looking at. Okay. So for example, suppose A is a matrix in 2 by 2 thing, and A is actually equal to 10, 9, 9, and 8. The matrix that we already looked at the other day, right? And then suppose you take X is equal to 1, 1. What is 2 norm of X? What is 2 norm of X? And you look at AX. So what do you get as AX? 19 and 17. So what is 2 norm of X? This I have not calculated, so I will need your help. What is 2 norm of X? 19 square plus 17 square. Can somebody tell me what is this?
Root of 650.
Huh?
Under root of 650.
Under root 650. And now, what am I really looking at? For this particular X, I am looking at this ratio. So what is the magnification that A is inducing in this particular vector? Root of 650 divided by root of 2, right? So root of 325, right? So that is the magnification that A induced in this vector. So what are we going to do? We are going to take any vector X which is not equal to 0, do this exercise, look at norm of X, look at norm of AX, and see what is the magnification induced. So for every X, there will be a number like this, right? So for every X, there will be a number. You choose maximum of all these numbers. You choose maximum of all these numbers. That maximum we are introducing, the maximum we are denoting by this norm of A. So this function basically is representing maximum magnification induced by A in the vector X. Correct? So what is the maximum magnification that you can induce? Do you understand geometrically what this number is? So I hope this exercise is clear. You understand this. So what was the other vector here which was shrinking really very much? Which vector was shrinking very much? Do you remember?
That was 1 minus 1.
So if you take X is equal to 1 minus 1, then what happens? What is norm of X? It's root 2. And what is norm of AX? What is AX basically? 10 minus 9 is 1, 9 minus 8 is 1. So norm of AX is also root 2. And what does it mean? Norm of AX by norm of X. What is happening? You are getting root 2 by root 2, 1. So there is no magnification. The length of X and AX, both these lengths are same, right? So that's what this number is saying. So you pick any vector X, and you see that this is what is happening. So under root of 325 is almost 18 point something, right? So this is roughly 18. So what this is saying is that the length is increased 18 times for this vector. If you take X is equal to 1, 1, then the length is increased 18 times. But you can see that trivially from here, no? X, AX. You see AX is almost 18 times bigger than X. So the length of AX is almost 18 times bigger than length of X. So this change in length, how the vector lengths are changing is what we really are measuring through this particular thing. So this particular norm, because you look at it from the action of A onto the vectors X, this particular norm is called as operator norm. Okay, this particular norm is called as operator norm. And now, once I write this down, the name operator norm, many people will have some prior connections to this concept of operator norm. So for example, math students who would have done functional analysis immediately will realize that a linear operator on a function space, right? You define operator norm exactly in the same way. Some people who are electrical engineers, they will remember you had looked at these transfer functions and you are talking of infinity norm or spectral norm of the transfer function. So what is a transfer function? It will act on signals, sines and cosines and all those signals that you have, right? So they are linear transformation. The transfer function represents a linear system. So you're looking at the operator norm only to see the norm of the transfer function, right? So these are different types of places where this operator norm already has occurred. You might have seen it already, but this is the importance and this is the geometrical significance, right? So instead of a vector x, you have a continuous signal or you have a function on which this operator is applying, and the same logic. How much is the magnification this operator induces in each signal it operates on, or how much is the magnification this operator induces on each function it is operating on, or in our case it is vector only x, right? So that is something that we are really looking at. So this is something that is really very critical. So this is the geometrical understanding. So now we have not yet proved that it's a matrix norm. We are just guessing that it might be a matrix norm. So in order to prove that this is a matrix norm, we have to show that all the four properties are actually satisfied by this particular function. But before going there, I just wanted to kind of give you the geometrical interpretation, so to speak. Okay, though I have not drawn any figure, but this magnification word actually brings in that geometrical sense, right? So you see how the lengths change, and you look at the ratio of the lengths, right? Length image vector divided by length of the original. So this interpretation changes. So in transfer function or signal processing, this is like energy in the signal, right? Or norm of the function on which it is operating and things like that. So this is something that you should understand. Any comment on this? So do you understand what we are going to do? So we are going to collect all such numbers. So one number is about 18, one number is like this. You collect all such numbers and you pick the maximum of those numbers, and that maximum of all those numbers is going to be that value. So the maximum magnification that this matrix A will induce. So any comments or any observations here? Have you prior seen this concept in any other subject? Can you tell? Apart from the two examples I gave, like functional analysis or transfer function things. Have you seen it anywhere?
Complex geometry.
In what?
In complex geometry, where a complex number was plotted on the argand, then we used magnification and rotation.
No, but how have you seen something like operator norm defined?
No, sir.
Okay, so I know of two things. If you know of any other applications where you used operator norm, please let me know. Okay, so I know two places I just told you.
Sir, is this norm efficiently computable? Like Frobenius norm we can compute directly, right? But this has a max term which can be difficult to calculate.
So there is this issue. Okay, so we'll prove that this is a norm, but then the thing is that how do you compute this norm? Because now this becomes an optimization problem, right? So this optimization problem does not seem like easily tractable. Unlike Frobenius norm, where you just have to compute sum of squares, right? And then take the square root. Computation was easy. Here computing the matrix norm is not as easy. So in general, computation of matrix norm is really very difficult problem as the size of matrix increases. In general, induced norm, okay, so this norm is also called as operator norm or induced norm. Okay, so this is induced norm because you are looking at the action induced by this operator on the vectors and then defining norm through that induced action. So this is called as induced norm also because it naturally involves this maximization term. You are right, your observation is very correct that in general computation of this maximum will be difficult. So in general this norm may not be easily computable, but so the thing is that you remember this matrix norm, induced norm. Now I can actually change this to any number I like between 1 to infinity, right? So I can write down p for any p between 1 to infinity, right? And it will still be a norm because p vector p norm you have here, right? So this is vector p norm that you see. So in general we will show p is equal to 1 and infinity. It is really very easy to compute this particular norm. P is equal to 2 we will show is related to singular value decomposition, so it is still okay. But in general for p which is not equal to this, this problem is a difficult problem. You have done a very good observation. In general, this problem is difficult, and people give estimate of this number generally rather than actually computing the norm value. Okay, so it's a difficult thing to compute. But some few simpler cases I will show you. Anything else? Okay, then in that case, let us try to prove that this indeed is a norm. Okay, so the first theorem that we want to prove is something which will help us in proving submultiplicativity property. Okay, so a vector, vector norm and its induced norm. Okay, so I will not use all these words, vector induced norm. So what I will really say is that 2 norm of Ax is less than or equal to 2 norm of A and 2 norm of X, where is maximum X not equal to 0, norm of Ax by norm of X. Can you prove this? So for X is equal to 0, trivially true, right? Because when X is equal to 0, you look at this particular inequality, norm of X is equal to 0. If X is equal to 0, Ax is also equal to 0. So 0 is less than or equal to 0, trivially true. So that's not a problem. So we consider this, right? So for any X not equal to 0, so for any X not equal to 0, you observe what I am doing. I am writing down norm of Ax, norm of X. Do you agree that this is less than or equal to maximum value of this? Do you agree that this is true? Is that okay? This proof is fine, straightforward, right? So when X is not equal to 0, this ratio for any arbitrary X is less than or equal to its maximum value, right? Just that observation gives me this particular result. This is important because this result will help me prove all the 4 properties of the, especially the submultiplicativity property. Submultiplicative property for matrix 2, correct? So that's why this result is really very important. Okay, so now what do we do to prove that this actually is a norm. Okay, so we need to prove 4 properties. So we'll start one by one. So the first property, how do you prove the first property? Norm of A is greater than or equal to 0 for every A. So norm of A is maximum of x not equal to 0. Norm of Ax is 2 divided by 2 norm. Numerator and denominator both are norms, so they are greater than or equal to 0. In fact, denominator is strictly greater than 0 because x is not equal to 0. So you are looking at maximum of all positive numbers, so that maximum has to be greater than or equal to 0. And in fact, if a is not equal to 0, in fact, if a is not equal to 0, then what happens? There exists a non-zero vector x, non-zero vector x, such that ax hat is not equal to 0. Correct? And you use this ax hat is not equal to 0. So norm of a is maximum of x not equal to 0, norm of ax divided by norm of x, and you know that this is greater than or equal to norm of ax hat divided by norm of x hat, which is strictly greater than 0. So the maximum has to be strictly greater than 0, right? So the first property actually holds true. The second property is trivial. I think you can prove this yourself. Mod alpha into norm of A. This property is very easy. No need to worry about this property. And the triangle inequality. So triangle inequality, how will it work? So let us see. So triangle inequality. So norm of A plus B. Okay, two norm is maximum of x not equal to 0. Norm of A plus B, its action of x divided by norm of x, which is same as saying maximum x not equal to 0, norm of x plus bx divided by norm of x. Now what will I do? I will use triangle inequality of vector norms in the numerator. So I'll get norm of ax plus bx divided by norm of x. Okay, so what triangle inequality I have used? Triangle inequality of vector norm, which we already know exists, right? Which we already proved. So this is what we have. So this I can write down as maximum x not equal to 0, norm of x by x plus maximum x not equal to 0, norm of x by x. This I can do because everything is happening for non-negative numbers, and this is basically nothing but 2 norm of a plus 2 norm of b. So every property that I have used here, I have used property of vector norms, right? So the vector norm which induces this matrix norm, I am using properties of those vectors, right? So that's what I have done. And this submultiplicativity is also not very difficult. Replacing x by bx, okay. Replace x by bx in the previous theorem. What will happen? Norm of abx is less than or equal to norm of a into norm of bx, which is less than or equal to norm a, norm b, norm x. Correct? So this is something that you get. And what
Sir?
is, yes?
Sir, in the proof of the first property, like you have shown the strict inequality, right?
Here, yeah.
Yeah, but it will be 0 when a is equal to 0, right?
It will be 0 when a is equal to 0, yeah.
So it is not a strict inequality. It is greater than or equal to 0.
So I said if A is not equal to 0. Greater than equal to 0, I already showed for every A, whether 0 or non-zero. Is it okay?
Okay, sir. Okay.
And this last property is nothing but maximum of x not equal to 0, norm of ABX divided by norm of x. So this is less than or equal to norm of A into. So we already proved this. Okay, so that's what helps us. Okay, so using this fourth, we can actually prove that this is happening. Is that okay? So one exercise I want you to quickly do and tell me. So I is identity matrix. Okay, identity matrix. Can you tell me what is Frobenius norm of identity matrix? What is true norm of identity matrix? Can you please tell me?
Root over n.
Root over n. And what is true norm of identity matrix? So you have to solve the maximization problem, right? Think about it. What is happening in the induced norm? You think about it. Is 1, right? Do you see that the norm is 1? Is that okay? Everybody understands why true norm of identity matrix is 1. Have you seen any other matrix whose true norm is 1? Have you seen?
Orthogonal matrices.
Yes. Why?
Yes. Because they don't change the magnitude of the vectors on which they will operate.
Correct. So this is also equal to 1, where Q in Rn by n is orthogonal. So what is the property of orthogonal matrices? You remember, for every x in Rn, what does orthogonal matrix have as its property? 2 norm of Qx is 2 norm of x. We had shown that, right? We had proven that. Geometrically, orthogonal matrices are not changing the length of the vector they act on, right? So obviously, if that is the case, then in the formula you can just substitute norm of Qx as norm of x. So what is happening here is maximum x not equal to 0, norm of Qx divided by norm of x, which is nothing but same as saying maximum x not equal to 0, norm of x divided by norm of x, because norm of Qx is same as norm of x. Length is not going to change. We have already proven that for all. So you are looking at maximum x not equal to 0, 1. So this has nothing to do with x. So this number is 1, right? So the 2 norm of orthogonal matrix is 1. 2 norm of identity matrix is 1. Identity matrix is a particular case of orthogonal matrix, right? So that is 1. But you notice Frobenius norm. Frobenius norm of identity matrix is not equal to 1. It is actually equal to root n, right? So there is a difference between the actual values of the norm, right? So the same matrix, like in case of vectors, you had different norms giving different answers. Different matrix norms also give different answers here. So I hope this part is clear to you. Is that okay? So once we have defined these matrix norms, once we understand geometrically what these matrix norms really do, let us see what is happening. Okay, let us see what is happening. So I will just write down one simple thing. Okay, so the reason why we started doing all of this is to be able to relate this with the sensitivity analysis, right? So we don't want to lose sight of that. So suppose Ax is equal to B. Okay, suppose A is in Rn cross n, B is a vector in Rn, and A is invertible. Okay. A is invertible matrix. So we know that there exists a unique X such that Ax is equal to B. Correct? There exists a unique X such that Ax is equal to B. Now assume, we will make an assumption, assume that B is perturbed to B plus delta B. Okay. So remember this B plus delta B, something similar we had done in the last class. Remember, I think I may have notes here. So towards the end of the class, you see B was there, A was this matrix, and B was this vector, right? So B was this vector. So this is the vector B that you want to start with. And then we slightly perturb this B vector to this vector, right? We slightly perturb this B vector to this vector. So B plus delta B, right? So that's what we have here. So B is perturbed to B plus delta B. Then let us assume the unique solution then I'll just write there exists a unique X hat such that Ax hat is equal to B plus delta B. I can say this. Why can I say this? I can say this because A is invertible matrix, right? I have started with this condition that the matrix A is invertible. So if A is invertible, then this is allowed. Okay. So suppose what do I do? Suppose define delta X such that X hat is equal to X plus delta X. Okay. So what we have here is A into X plus delta X is equal to B plus delta B. Is that right? And what will that really tell me? That will tell me Ax plus A delta X is equal to B plus delta B. But we know what is Ax from equation 1. From equation 1, what we can say? From 1, what do we get? We get A into delta X is equal to delta B, which means that delta X is equal to A inverse into delta B. Is that okay? This calculation, all of you understand so far? So what am I really going to do here? What am I really going to do here? What am I really going to do is that I am going to say that if delta B is very small compared to B. So when I say very small compared to B, I am talking in terms of norms, right? I want to say that delta X is also very small compared to X. I want to make a statement like this. So can I make a statement like this? The answer is obviously not, because we have seen an example in the last class that the delta B perturbation was comparatively very small with respect to B. But change in X, which was delta X, was really very large compared to X, right? So we obviously cannot make such a statement. But can we say in what cases this change will be really very small and things like that? That's what we are really trying to understand. Okay, so this is 1, this is 2, this is 3. So now what will I do? From 3, Okay, so from statement 3, what can I say? Norm of delta x, I'll take 2 norm, is equal to norm of A inverse delta B, it's 2 norm, which is less than or equal to norm of A inverse norm of delta B. Is this statement clear to you? What I have done? How do I arrive at 4? Which result I have used? Which property I have used?
Submultiplicative.
Not submultiplicativity, basically this theorem. Any matrix A and any vector x I have, then the product Ax is 2 norm is less than or equal to matrix 2 norm times vector 2 norm, the one which is with the arrow. This is the property that I have used, right? So in the example that we are looking at, our matrix is A inverse and our vector x is delta B, right? So A inverse and delta B. So that is what I have. Is that okay? So delta x, 2 norm of delta x is less than or equal to 2 norm of A inverse times 2 norm of delta B. Further, I want to do the same thing. From 1, what can I say? B is equal to x. X is equal to B, same as saying B is equal to x. So this implies that norm of B is equal to norm of X. This I can write down is less than norm of A into norm of X. So this is my statement 5. And now what am I going to do? So this 5 I can rewrite. Okay, so this statement I will write down as 1 upon and I just multiply 4 and 5. What do I get? This is your first sensitivity analysis result. Okay, this is your first sensitivity analysis result. And now you see why I wanted to introduce matrix 2 norm. I wanted to introduce matrix 2 norm, that induced 2 norm here, because it is coming out here. So now you see what I have really done. So what is this bracketed statement saying? Okay, this is very important. What is this bracketed statement saying? Norm of delta B is absolute value of the perturbation in B that you. But when you look at this ratio, norm of delta B divided by norm of B, when you look at this particular ratio, so do you agree that this is telling me what is the relative perturbation, the quantification of relative perturbation that I given B? It is much better to talk in terms of relative perturbation than exact value of the perturbation. And the same thing I am looking at the left hand side. I am saying that what is the relative perturbation I am getting in X because of delta B. So delta X is the perturbation in X that I am getting because B is perturbed to B plus delta B. Do you all agree? So that is what this is. And now I am saying that this value, the value which is of interest to us, the relative perturbation in delta x by x, this value is not only bounded above by the relative perturbation that you see in delta b by b, that is obvious, it has to depend, but it is scaled by this particular number. Okay, this is scaled by this particular number, and this particular number in red highlighted thing is actually called as condition number of matrix A. Okay, so this number is actually called as condition number of matrix. So this condition number is actually scaling. This condition number is actually scaling the relative error in B. And once the relative error in B is scaled by this condition number, that works as an upper bound for this relative error in delta x by x. So if the condition number of matrix, which is nothing but product of 2 norm of A times product of 2 norm of A inverse, if you multiply these two numbers, if the condition number, if the scaling factor is really very high, if it is really very high, then what does it tell? It tells that if you have slight perturbation in B, there is a chance that the perturbation in X is also going to be really very high. What is the extreme case? What is the best possible perturbation number? I don't know. But let us think of orthogonal matrices Q. Suppose you are working with a system of linear equations Qx is equal to B. And then you did Qx is equal to B plus delta B. Now you have two norm of Q and two norm of Q inverse. Because Q is orthogonal matrix, two norm of Q inverse is two norm of Q transpose, which is 1. So this condition number for orthogonal matrices is 1. So if the condition number of orthogonal matrices is 1, then there is no scaling happening to the relative error in B. And you are saying that relative error in X is bounded above by relative error in B. So if you give a very small perturbation to B, you can expect a very small perturbation in X also. Whatever perturbation in B you give, it doesn't matter, because the scaling of the relative perturbation in B is 1, because condition number of orthogonal matrix is 1. But on the other hand, if this condition number is really very high, so we will see some properties of condition number in next class. So if the condition number is really very high, then you can see that this perturbation delta B by B, relative perturbation, even if it is really very small, the condition number can magnify it and you will get really very high relative error in delta X by X. And now we can suspect that this is something that might have happened in the example that we were looking at here. The example that we were looking at, something like that might have happened, right? A very small perturbation in B resulted in a very large perturbation in X. And now we understand the formula. What is the formula? The formula that governs these perturbations. It governs the upper bounds of this perturbation is given by this. So that means that the condition number of the matrix probably is really very high. So this is your first sensitivity analysis result, and we hope to derive similar such results in sensitivity analysis and try to understand how this system of linear equations behave when you give perturbations. So these condition numbers and this sensitivity analysis result can be very nicely connected with the regression problems also. So we'll try to do that little later, and we will see principal component regression and all, and how do those things really help us further. Right now, this is the first baby step towards doing that. And do you understand this? What we just did, is it clear? So as this example suggested, I give a very small perturbation. So very small meaning relative perturbation I'm looking at. So now if you see here, if you see in this particular example, B is equal to 1997, correct? And delta B is actually equal to 0.01, 0.01. Correct? So that is my delta B. So you can see norm of delta B divided by norm of B. This is like really very small. This is really very small. And that small perturbation, now you see here in the notation of the theorem, delta X is also 0.01 and minus 0.0, right? So that is the delta X that you got, and X is equal to 1, 1 in the notation of the theorem that we had. So reasonably small perturbation in X also. Here also, in this particular case, your B was same, but delta B is different, 0.01 minus 0. Okay, the other way around, minus 0.01 and 0.01, right? So if you see, the magnitude of the perturbation in both the cases is same. But that same magnitude perturbation creates havoc in this, right? So the direction of the perturbation delta B has to do with something. Can you see from this and tell me what the direction of delta B is really doing? From equation 3, can you relate what might be happening? you think about this equation 3 that you see here and these different delta b's that you are having here and the relation of this delta x is equal to A inverse delta b, then can you say that it is not necessary that for every delta b of the same size you need to get same perturbation. The direction is also really very important. In fact, the whole game is based on the game of directions. So what directions you choose and what directions you do not choose in perturbing b, that actually result in whether you will get a very bad delta x or a very good delta x. So can you see from this equation 3 and say what might be happening? So this is something that is your homework. Okay, this is something that I want you to think about. So this equation 3, try to think about this equation 3 that you see here with the example that I am trying to show in the previous class, and try to connect these concepts and tell me what might be really happening. Okay, so this is kind of your homework. You think about it today and we will start our discussion tomorrow from this point. But before we close, any doubt about what we have done so far? Anything that you want to add to the discussion that we had today? Okay, in that case, we can stop and we will continue this in tomorrow's class. Thank you.